Hey everybody, we're going to continue with Chapter 5, and we're doing Section 5.2 today, and we're going to be talking about vocabulary associated with polynomial functions, and this is notes number 25. So we're going to look at a polynomial function in general, and then I'll give you an example. So in general, a polynomial function has terms. A sub n times x to the n is a term. A sub n minus 1 times x to the n minus 1 is a term, etc. So basically each term has a coefficient. Those coefficients are the numbers in front of x, and those are being referred to as a sub 0, a sub 1, a sub 2, all the way up to a sub n. And those numbers have to be real numbers. And then you have x raised to a power. And those powers, or those exponents, have to be whole numbers. So we have x to the n minus 1, etc. on down. So an example of this would be f of x equals 4x cubed minus 7x to the 6th plus 2x minus 1. And I purposefully wrote the terms out of order. See, you might expect them to be in descending powers of x, and if they are in descending powers of x, it's called standard form. But I purposefully wrote it this way because of the example I want to work through as we go down this page. So that's an example of a polynomial. You see that each of my coefficients are whole numbers. Sorry, not whole numbers, real numbers is what I meant to say. So you could even have a number there like pi, or square root 2, or something like that. And you see that each of my exponents are whole numbers. 3, 6, this one has a 1. And then how about this last term? You could imagine that it has an invisible x to the 0 on it. So each of those exponents are whole numbers. Okay, let's talk about the degree of the term. The degree of each term is the power of x for that term. The power or the exponent value. So, in my example, I have 4 terms. The degree of the first term is 3. The degree of the next term is 6. The degree of the next term is 1. And the degree of the next term is 0. Now let's talk about the degree of the polynomial. That would be the highest exponent or degree. The highest exponent or power, I should say. So, if we look at my example, 6 is the highest one, so the degree of the polynomial is 6. If we're looking at the general equation, then n is the highest one, so the degree of that general one is n. The leading coefficient is the coefficient on the term with highest degree. So, don't be misled by the word leading. That's kind of a pun, actually. It's not always the one that occurs first. It's the one on the term with highest degree. So looking at my example, the term with highest degree is negative 7x to the 6th, so negative 7 is my leading coefficient. You could also be asked, what is the leading term? So for my example, the leading term would be negative 7x to the 6th. That's the whole term with its coefficient as well as its x to a power. Okay, so we have names for different kinds of polynomial functions. We've already seen some of these names as we've worked our way through Chapter 4. So I'm going to jump ahead a little bit. In Chapter 2, I want to say, we saw that linear functions have degree 1. So, for example, that would be like y equals 3x plus 5, because it's x to the first power and there is no higher exponent, and so the degree is 1. It's linear. And then in the last chapter, we saw that quadratic functions have degree 2. So an example would be y equals negative x squared plus 7x minus 4. The highest exponent is 2. All the exponents are whole numbers. All of the coefficients are real numbers, so that is a polynomial function. Now, if the degree is 0, that would be like having just y equals 3. So you could imagine an invisible x to the 0 on there. But if it's not there, typically it won't be written in. It's just y equals 3. That is called a constant. If you were to graph it, you would get a horizontal line. Every point has the same y value. It's a constant y value. Okay, the names for the next 3 are, if it has degree 3, it's called cubic. If it has degree 4, it's called quartic. You can think of like quarters, 4 quarters in a dollar, 4 quarts in a gallon, 4 quarters in a football game. And if it's degree 5, it's called quintic. You could think of quintuplets, 5 babies all born at the same time. And so the highest power on a cubic would be 3. Let's just make something up. It could be as simple as y equals x cubed, or maybe it has other terms. The highest power on a quartic polynomial would be 4, so we could make up something more complicated here. Maybe it's y equals 7x to the 4th minus 2x cubed plus x squared minus 77x plus 42. Threw in 42 for Forrest. I knew he would like that. As long as the highest exponent is 4, you can have other terms or not have other terms. And then quintic, I'll just keep this one simple. Let's say this is y equals 10x to the 5th minus 9. As I said earlier, standard form is written in decreasing powers of x. So I believe that I've written all of these examples in standard form. Okay, now we have an example, and it's okay with me if you don't write this down, but what you might want to do is pause and see if you can figure out the answers before I talk through them. So the question is, are the following polynomial functions? Yes or no? If yes, find the degree, the type, and the leading coefficient, and if no, state why not. Okay, so pause if you're going to figure them out for yourself. And for part A, notice that we have an exponent that is not a whole number. 1/2 is not a whole number, so this is no. Not all exponents are whole numbers. And for part B, let's check out our exponents. We have 5, 4, we have an invisible x to the 0 here. We have, oops, that's not a 4, that's a 2. I don't know my numbers, do I? 5, 2, 0, 4. Those are all whole numbers, so it meets that criteria. And then we have coefficients, real number, square root 10 is a real number, 1 is a real number. So yes, it meets all the criteria to be a polynomial function. What's the degree? Well, what's the highest exponent? 5, so the degree is 5. What's the type? Since it's degree 5, it is quintic. It's a quintic polynomial. And the leading coefficient would be the coefficient on the term with highest degree. So that would be -8. Okay, let's look at part C. Let's look at those exponents. 3 is a whole number, 2 is a whole number, and then 0 is a whole number. So it meets that criteria. And let's look at the coefficients. 1 is real, -4/3 is real, -1 is real. So yes, this is also a polynomial function. The degree is 3 because that is the highest exponent. And then it is cubic. And then the leading coefficient, which is the coefficient on the term with highest degree, is 1. Okay, part D. Let's look at the exponents. 4 is a whole number, but -2 is not a whole number. So we can stop right there and say no, this is not a polynomial function because not all exponents are whole numbers. Okay, So we're kind of getting into part 2 of our lesson now, and I don't know if you can see that the whole phrase at the top, it says evaluating polynomials. To evaluate means to put a number in there and see what you get out. So let's say for number 2 here we have this cubic polynomial f of x, and we're interested in finding f of 2. Well, we already know one way to do that, and we can call that substitution or direct substitution, and we can casually say just plug it in. So let's plug in 2 everywhere we have an x. So we have negative 3 times 2 cubed plus 2 squared minus 12 times 2 minus 5. And we're just going to compute that, and for that I got negative 49. Now I want to show you a second method. I'm not saying the second method is necessarily easier, although you might think so, and maybe sometimes it is, or maybe sometimes you choose to do it because you like it better, but it's going to get us somewhere eventually in this chapter. Using this method is actually taking us someplace we need to be. So even if we don't need to know the second method just for the sake of evaluating, we need to know it to be ready for something else that's coming. So it is called synthetic substitution. And before I tell you what to do, I'm going to tell you kind of why it works. So you don't have to write these steps down, but this is the math behind why synthetic substitution works. So let's just take this polynomial function that I was using earlier in problem 2, and I'm going to modify it slightly by factoring x out of the first 3 terms. So you see that this term has a factor of x, this term has a factor of x, and this term has a factor of x, but the fourth one does not. So I just factored the x out of the first 3 terms. Okay, why? Well, it doesn't seem like there's any reason for that yet, but you have to kind of wait and see what happens next. Now we factor x out of the first 2 terms. So notice that these 2 terms both have an x in them. You can factor x out, and we end up with this. Now you would keep doing this process until you get down to the point where you only have a single term with an x in it, which is kind of where we are right now. So if this started out being like 3x to the 7th, you might have to do this thing 6 times until you got to this point. Well, you wouldn't do it. You're not actually going to be doing that factoring step. This is just me showing you the background for why this process is going to work. So now that we have this modified form of our expression, what we can do is find f of 2, and here's the recursive process. Recursive means like you're doing the same sequence of steps over and over again. Iterative is another word that means the same thing. So you take your number that you want to plug in. You take 2. You multiply it by the first coefficient in your problem, which was negative 3. Whatever you get for that, you add the next number, which was 1. Okay, now that's your result. You take that result, you multiply it by your number 2. And then you add the next number in the problem, negative 12. You take that and you multiply it by your number 2. And then you add the next number in the problem, which is negative 5. So over and over again, you're taking your number 2, multiply it by the number in the problem, add the next one. Multiply it by 2, add the next one. Multiply it by 2, add the next one. And just to double check, what do we have here? We have negative 6 plus 1 is negative 5. Negative 5 times 2 is 10. 10 minus 12 is, negative 5 times 2 is negative 10. Negative 10 minus 12 is negative 22. Negative 22 times 2 is negative 44. And negative 44 minus 5 is negative 49. Okay, so we need to see that again. But what I'm going to show you is how you're actually going to do it. You're going to do a process called synthetic substitution that has a shortcut method. So here's your shortcut for showing steps with synthetic substitution. Take your number that you're plugging in, 2. Put it in a little box. Take your coefficients from the problem, negative 3, 1, negative 12, negative 5. Put them in a row. You don't have to write the x's in. We start with the first number. We bring down the first number, negative 3. We multiply it by the number in the box. Negative 3 times 2 is negative 6. We write it down. And then we add the column, negative 5. Take that. Multiply it by the number in the box. We get negative 10. We write it down. Add the column. We get negative 22. Take that, multiply it by the number in the box, we get negative 44. Write it down and add, we get negative 49. So this just kind of streamlines it for us, and you get into the motions of it and it goes really fast. And I'm not saying you always have to do it in your head. Like, you can use a calculator to crunch these numbers when it gets to the point where it's too hard to do it just quickly in your head. So let me go through that with you again with examples 3 and 4. So here's number 3, a different polynomial function. We're going to find f of negative 2 using synthetic substitution. So I put negative 2 in the box. Then I put the coefficients of my polynomial in a row. 1x to the 4th, 2x cubed, 3x squared. Okay, there's something special here. 0x. Notice that there's no x term. You have to put 0 in to hold its place. And then negative 7. Bring down the first number, multiply it by the number in the box, write that down, and add the column. Multiply that by the number in the box, write that down, and add the column. Multiply that by the number in the box, write that down, and add the column. Multiply that by the number in the box, write that down, and add the column. That last number 5, that's your function value. F of negative 2 is 5. If you don't believe it, take negative 2, plug it into f of x, and see what you get. Let's do it again. For number 4, we're finding f of negative 1. Okay, the terms are in descending powers of x. We are missing 1. We're missing x to the second power, so put a 0 in there for it. Negative 1 in the box. Coefficients, negative 2, negative 1, 0, 4, negative 5. Bring down the first number. Multiply it by the number in the box. We get 2. Write it down and add. Multiply that number by the number in the box. Write it down and add. Multiply that number by the number in the box. Write it down and add. Multiply that number by the number in the box. Write it down and add. Negative 10. So f of negative 1 is negative 10. Okay? Now, if you had something like, let's say you were finding f of 3, and f of x was x to the 4th plus x squared, you do need to have your placeholder 0 for your x cubed, but you also need to have a 0 for your x to the 1st and a 0 for your constant. So this is your x to the 4th, this is your x cubed, this is your x squared, this is your x to the 1st, and this is your constant. You need a place for each of them. Okay, we're going to tie this together to end this lesson. We're going to tie this together with graphing and end behavior. So if you remember in our last lesson from section 5.1, we did a calculator activity and explored end behavior. So let me just remind you that we found that if it was an even exponent, or even degree polynomial, x squared, x to the 4th, x to the 6th, etc., and with a positive leading coefficient, then both ends would be up. If it's a parabola, well, we're familiar with that, but it might also be something like this, or it might also be something like this. You just don't know. We haven't gotten into that much detail yet, but they're going to open up. And we learned that if it has an even degree but a negative in front, then both ends go down. Could have other terms, but we're not concerned in this conversation right now about what's going on in the middle. We're concerned about what's going on at the ends, so both ends down. Could be something like this, could be something like this, both ends down. And then we learned that if it's an odd degree polynomial, so x to the 1st, x cubed, x to the 5th, etc., then it's going to be like a line with a positive slope where we have the left end down and the right end up. And then if you have a negative leading coefficient, just like a line with a negative slope, it's going to be the other way. So, let's look at what we have here. We have an even degree polynomial. It's quartic. It's x to the fourth. We have a negative leading coefficient, so both ends down. And we said something like this last time. F of x goes to negative infinity as x goes to infinity, and f of x goes to negative infinity as x goes to negative infinity. Now, we know that, and we're also going to plot some points to get a rough idea of what this graph looks like. We're going to build on these ideas as we go through this chapter, and we're going to get more and more information to help us graph, but for now we're just using synthetic substitution to get us some points and the end behavior. So what I'm going to do is to find f of negative 3, I'll put negative 3 in the box, and the coefficients, negative 1x to the fourth, 4x cubed, negative 1x squared, 0x, and 6. And then bring down the first number, multiply by the number in the box, write it down and add. Multiply by the number in the box, write it down and add. Multiply by the number in the box, write it down and add. Grab my calculator, multiply by the number in the box, write it down and add. So that means that this is going to go through the point negative 3, negative 192. Now I'm going to pause and I'm going to find the rest of those values just so you don't have to spend the time watching me find them all. You can also find some of them for yourself to practice this technique. Okay, so what you see now is that I've done all of the synthetic substitution to find all of those y coordinates, those function values, and now I'm going to plot the points. So for negative 3, negative 192, I decided to make my y scale not go quite that far, so I'm just going to make that point way down here. It's kind of off grid, I'll say. Negative 2, negative 46, something like that. Negative 1, 0, 0, 6, 1, 8, 2, 18, 324. Okay. Now, it's coming up from way down there. It's going up, and remember the end behavior that we described? It's supposed to go back down. We just haven't gone far enough to find where it does that. So I'm just going to kind of do something like that for now. Okay. So there's kind of a little introduction to graphing polynomials, and like I said earlier, we're going to get more detail as we go through this unit. The main point of today was practicing synthetic substitution. And here is your homework. Thanks, everybody.